Hi, everyone. First, I want to thank the organizing committee for their efforts to organize this wonderful CALPHAD Global Conference. In this presentation, I'm going to talk about the next 50 years of CALPHAD, where we all know predicting future is difficult, but let's see, based on what we have now, what the next 50 years may be or may look like. My name is Zi-Kui from Pennsylvania State University. And then last year, the National Academy of Engineering celebrated the 50th anniversary for one of their publications, The Bridge. Professor Sinod and I wrote an article for this special issue to discuss what will be next 50 years for the design of new materials. We all know that materials are closely related to human civilizations. And we talk about the prehistory of humanity. We had a Stone Age. The human used the natural materials. Then we had a human-made material, copper, tin alloys, which we call the Bronze Age. And after that, we had Iron Age. We used the human-made iron carbon alloys. And that made a big change of our civilization. What we call it industrial manufacturing materials 1.0 to 3.0. Concerns steam power, electricity, and computers. We all say now that we're in the industry 4.0, it's industry manufacturing materials 4.0. It is about digitization. So basically digitize everything. Well, digitization is about data. Well, it's more about knowledge. Right? We'll put our knowledge into digital form. And then let's look at manufacturing. We know that manufacturing is a process to form the products, use some material to serve one or two functions. And it's about changing materials, right? Liquid, solid. So talk about it concerns phase stability. So what represents the phase stability or the knowledge of phase stability and functionality is thermodynamics. We know that in 1870, Gibbs established the combined law of thermodynamics. So it was until 100 years later that Kaufman proposed the CALPHAD to digitize thermodynamics. So thermodynamic knowledge becomes digital. And in another 50 years, we've been practicing CALPHAD, and like the presentation by Greg Olson and Jim Yoko, for the application, design materials. So what will be next 50 years for CALPHAD, or in general, for the knowledge, digitization of thermodynamic knowledge? Okay, let's look at what the CALPHAD model is about. CALPHAD modeling concerns the Gibbs energy, modeling of Gibbs energy of individual phases as a function of temperature, pressure, composition, and even more importantly, is Kasai here. So Kasai represents the internal degree of freedom. Okay. So that means it's not only equilibrium, it could be non-equilibrium state. And we know that we use derivatives of Gibbs energy. There's quantities like heat capacity. We call them some chemical data, heat capacity, enthalpy, entropy, activity, and so forth, to derive the free energy function. In principle, there should be, those quantities can completely determine the free energy. However, the uncertainty of those free energy functions are large. So you cannot really predict the phase stability accurately, not in the accuracy we need for materials processing. So to improve those functions, then we need to use another set of data we call phase equilibrium data, with phase stability, phase boundary, or tie lines, as Greg also mentioned in his talk, and also by J.C. Zhao basically at the equilibrium state. So there's no driving force for this process. So we'll get this process. Then we start with pure elements. We make it to the binary, to ternary, to multi-component system. So after we create this database, then we can do material design. Material design concerns equilibrium. Well, that's important. It also can use to, it also concerns driving force, right? For the driving for the precipitations. And in addition to, you can also do the physical chemical properties, which are secondary derivatives of Gibbs energy, or free energy in general. As you will see, that is beyond heat capacity, enthalpy, entropy. Is a wide range of properties we can predict for the derivatives of the free energy functions. Okay, so CALPHAD is about the models for the properties of individual phases. Well, we focus on the free energy function. And the CALPHAD is community. We have a website. We have a conference, annual conference started in 1973. We have a private foundation, CALPHAD Inc., since 1975. It supports the scholarships and awards for the community, and it supports conferences too. And we have a journal, CALPHAD Journal, since 1977. And then to do CALPHAD modeling, of course, we need tools, and we created databases. And we have commercial tools. There's a special issue in CALPHAD, volume 26, issue 2. Had a number of papers on the software tools we have, including commercial ones, SummerCalc and FactStage, CompuSum with Pandat and GeoMet Pro and MetaCalc. And since that time, there have been some open source codes too. OpenCALPHAD, Thermochemica, and also HiCALPHAD SBay, which are developed in my group. And it has the capability to high throughput CALPHAD modeling with uncertain quantifications. Okay, I do want to mention that CALPHAD supports the ICME and MGI. And it is because of CALPHAD inspired me to coin the term material genome in 2002, and which is discussed in this paper I wrote in 2014. As Greg mentioned, in 2004, there was a publication on accelerating technology transition and discussed about the material genome concept, even though it didn't have the term at that time in that report, but inspired by the Human Genome Project. And also 2008 is a publication of integrated computation materials engineering. In that report, it is stated, CALPHAD software is arguably the most important and perhaps the only generic tool available for ICME practitioners. That just is the importance of CALPHAD modeling. And then 2011, there's Material Genome Initiative. Greg and Charlie Kuhlman wrote an article in 2014 on materials genomics from CALPHAD to flight. So CALPHAD has been very useful and for material design and for materials processing. As we know, as I mentioned, the CALPHAD model starts with pure elements, go to binary, ternary, and so forth. So it also gives us a challenge here. The challenge is that if we change the property of one component system, then we have to change all the properties, all the systems involve that element, all the binaries, all the ternaries. As you can see that for this 6-component system, and there's a lot of systems we have to remodel, how to change the parameters. So that's very, very challenging and very, very difficult. And this is reflected by this chart, which it was in Richard Otis' PhD thesis. It basically it indicates that it's a one-way information flow. So we collect the data with the experimental DFT, We translated them into the software format. And then during this transition, we lost a lot of data, information, metadata. And then when we get the data, we do the modeling. Is the iteration, okay, iterative process. So then we got the parameters. Now, when we got the parameters and all the history and also the metadata lost, we got a database. So you can see a lot of information is lost during the process. So making it extremely difficult to remodel the system. Okay, so we have to think about this one, how to improve it. So we developed a CALPHAD and SBA to do that work. And in 2018, I wrote a paper called Ocean of Data. So really summarize this kind of idea. Okay, the idea is that we need to integrate the first principle calculations, CALPHAD modeling with machine learning, and at the same time create an ecosystem for data. So when I talk about this idea, my idea with a communication staff in our college, she came up with this very nice diagram. Talk about the data ecosystem. Okay, so what it means is that we have a lot of data. Talk about data lake. We talk about the data stream. Okay, we talk about the company secret data, right? Proprietary data. But we, in principle, we should be able to collect all the data together, well, connect them, and then we can use CALPHAD and SBA to develop a databases, high throughput, and the database will into the cloud, and then they will be condensed again, right? Precipitation, and then go through this cycle. Okay, of course, they also go to the lakes, go to the stream, and also go to the ocean. Then we should take this kind of cycle, a data ecosystem. So that's about ocean of data. So that's what I think is the future of CALPHAD. Talk about data application. So I wrote another paper last year about computation thermodynamics and its applications. Thermodynamics is way beyond the phase stability. Okay, of course, it's very important. So stability and metastability and instability. And actually those can be used to discuss across the phenomena. I'm going to hopefully have time for a few examples. Seebeck coefficient, Sorority coefficient, piezo ferroelectric properties. Okay. It concerns transport properties, diffusivity, conductivity, and even goes to mechanical properties like elastic properties or even plastic properties. Okay, now the question is really, as many people think, that is thermodynamics for equilibrium only. Well, if you look at it, the first law, no, it's not, because the first law never says whether the system should be equilibrium or not. However, if you look at the function by Gibbs in 1870s, that's for equilibrium, because the equation he had is du, which you know is TdS minus PdV plus summation of mu I dni. This is for equilibrium only. So what's different between these two is another term. Okay, it's entropy production. So if you add entropy production in this equation, then it becomes for non-equilibrium system. It's applicable to non-equilibrium system too. Okay. So now if the Gibbs energy or just switch variable, you see, now you have to add one more term. Okay, that's entropy production for internal processes. Okay, so that's what CALPHAD is about. So CALPHAD modeling is really for non-equilibrium systems, non-equilibrium thermodynamics. Okay, we can say that. Okay, the CASI here is internal state variables. Like when we sublattice model, it's side fractions. Okay, side fractions. And in the afternoon today, June 24th, I will give a seminar called Entropy, a title is Entropy. Well, the Duke University, well, virtually. Now, if you're interested, you can sign up, and it's linked. Then in that presentation, I will talk about details, but the definition of entropy, how we use it, what its implications, what can we do more with it. Okay, now I mentioned that thermodynamics is not only about equilibrium, it's actually a lot of properties not only heat capacity. Heat capacity is one of them. So we in the equation I showed before, we have X for the molar quantity, Y for the potentials. Now it's the derivative between these two, give a wide range of properties. Of course, heat capacity is here, okay? Elastic constants, permittivities, permeabilities, okay? They're all from the derivatives. It's the second derivative of energy. It's the first derivative between X and Y. So Y is here and X is there. So some expansion by the derivative, and all these coefficients are all in the derivatives of the free energy function. Now it's important here, the diagonal terms, they are always positive for stable system, for stable systems, but the off diagonal terms could be positive or negative, or zero, or infinite. Okay, of this diagonal can also be infinite too. But this could be negative or positive. Okay, so but the diagonal terms will always be positive for stable system. There are actually another type of new derivatives we have been discussing. I actually find it very interesting. It's the derivatives between the two potentials. For example, between the stress and the temperature. Okay. Or look at the last item, last row here, the chemical potential to temperature derivative. What's that? That's the thermal transport property. Because temperature driven chemical potential, driven diffusion, or driven electron migration, that's some electrical property. Okay, so you can see this this derivative again is a second derivative of energy, actually has a lot of properties, which sometimes people think is kinetic, they are kinetic properties, but it's actually thermodynamic properties. Now, I do want to emphasize about this internal variable psi is very important. Okay. For example, when we do CALPHAD modeling, we talk about the non-stable lattice structure, BCC copper. Right? BCC copper, we need BCC copper is not stable, we know that. However, BCC copper can form in a BCC solution between iron and copper. Okay? So we need a free energy for the BCC solution, which needs the BCC copper free energy. And then BCC copper free energy, which depends on the FCC, and we call it lattice stability. So that's the foundation of CALPHAD modeling. And there's a lot of other internal variables like the mole fraction, side fraction, order disorder, and the polarizations, and the defects. Defects actually you think about defects, they're actually internal degree of freedom, right? Dislocations, vacancies. Some of them are stable, some are less stable. Okay. The twins and the stacking faults and green bond, they exist there, right? They stay there. Okay. So those defects are very important if you want to talk about the properties. Mechanical properties depends on dislocations, vacancies. So these internal variables are very, very important for us to understand the materials. Okay, before maybe 20 years ago, the CALPHAD modeling is take experiment data and some estimations, put together, we do the modeling, we develop databases. 20 years ago, first principle calculations became available to us. But we know first principle calculations are most for zero degree Kelvin. Now you will put a statistical mechanics to define a temperature. Now you can see that we have experiment, we have first principle calculations, we get a statistic together, we can do a much better modeling. So it enhances the predictive power of database. As I mentioned, we have tools and database, so forth. Right now, database can be better. Of course, it also gives us a problem because now we can revise the database we had before, which we had 10 components or 20 components already, right? How can we revise the databases? Okay. So we need new tools. Okay. We need high throughput tools. Okay. We need uncertainty quantification for our predictions. Okay, so in my group, we have this a GitHub repository. All codes packages are open source. So they're divided into two groups of it. One, data generation. So I have machine learning code. We have DFT tool kit for French, for high throughput calculation. So you can go to download it. And then we have data processing. We got the data. Then we do the use CALPHAD, can define new models. Okay. And the SPA can do the parameter evaluation and with uncertainty. Okay. And we also now created workshops, and the Material Genome Foundation is one of the nonprofit foundation we formed, and to promote this open source tools and for the community to adopt. And we do have in this YouTube channel, we have a number of recordings we had from previous workshops. Next week, Monday and Tuesday, we have another workshop for these tools. And the sign up sheet is available as the next slides or so. Okay, so now we got data generation, right? We got data processing. So we now want to create a data ecosystem. So we take the theoretical data, we take experiment data, we call them proto data. Okay, we call them proto data. That's machine learning, DFT, ab initio modeling dynamics, FEM, and experiment. And we use CALPHAD aspect to generate CALPHAD databases. Then you can do material design, and material processing, and the material service, put in the applications. And in that process, we generate new data, right? The new data will fit into the proto data system, and then it goes through this cycle to improve the database. Okay. Of course, another thing is that when materials get used up, you can recycle it. The recycle will generate new data again. Okay, so now the idea is that because this ecosystem, the new data continues getting into the proto data system, and it continuously improves the CALPHAD databases, and then continues for the new material design and the manufacturing, the service, and the recycle. Now, once I show our DFTK, is www.dftk.org. That's an open source high throughput DFT code to calculate the free energy. Okay, it builds up on the high throughput tools in the community, Pymagen, Fireworks, and the Custodium. This and Automate. They are used also for materials project. And then on top of that, we build this DFTK to do finite temperature and finite and variable compositions. Okay, because for CALPHAD modeling, we need temperature dependent, we need composition dependent. And DFT-based calculations are very good, very useful. However, it still takes time. So we want to make it more efficient. So you can take the DFT data, calculate data like, for example, the OQMD database or the materials project or other databases. When developers train the new neural network, okay, they're going to make predictions. Okay, make predictions. So there's one of the code we developed in the last 2 years called Superfin. As I showed on the website, you can download it from the website to use it. And you can see how good the machine learning models are with the database from the DFT databases and the predicted one. And you see the maximum absolute error is like 28 MeV. Okay, so it's in the accuracy of the DFT calculations. And also you can take your new data to do so-called transfer learning to improve the model. Like new data which is not in the system. We're continuing to improve this tool. And now you got this big database, you get the machine learning models. You got a lot of structures. So we wanted to be able to put them together. Okay. So we're going to calculate in machine learning, you have the data, algorithm, and descriptors, right? So we're going to calculate descriptors for all the structures. Like we created one called materials property descriptor database. So that means that in the future, when you get a new structure, it'll be much faster than now use machine learning model because the descriptor calculations takes the most of the time. So you can handle millions of structure very efficiently. And it's automatic processing of all available data. And the more important is that you can decentralize. It doesn't have to be do one computer, centralized computer. It can be different cloud resources. We're going to release this one very soon in the summer. You will be able to see it from our GitHub repository and also on our group website. Okay. Now you got all the data, right? So want to speed up the development of the database and also use machine learning. Okay, so we develop a code called aspect. It's high throughput modeling. Basically, evaluate the kind of model parameters. We're doing the 2 steps. The first step is use the derivatives only, the friendly derivatives. As I mentioned before, the derivatives in principle can get a complete database, right, with all the parameters in the friendly function, basically do integration. Okay, but you have to make sure that you don't overfit. So it's a balance between number of parameters and the robustness of the model. So develop a algorithm for that. Now you get the initial set of data parameters now, right? So you can calculate phase diagram, all the properties. But we know that the prediction of those models are not very accurate, particularly for phase stability. You could be 100 degrees off. So you need the second stage is use of phase equilibrium data and refine the model parameters with Markov chain Monte Carlo method and Bayesian parameter estimation. When you do the Bayesian parameter estimation, you get uncertainty quantification too. So in order to be able to do this kind of thing, we need a computing engine. Okay. And about 6 years ago, we started to develop the CALPHAD, which is was a PhD thesis of Richard Otis. It used advanced sampling algorithms to find the sampling, the starting point for calculations. And the very important thing of the CALPHAD is use symbolic computing in Python. You can develop new models. For example, we just recently implemented the quasi-chemical model into the CALPHAD. And in the future, it will be very easy for anybody to develop new models. So now let's think about this one, right? We not only the model for some dynamics and also other property models too. And now remember that we talk about the internal degree of freedom, right? So you do equilibrium calculation, you minimize it, the internal degree of freedom is eliminated, they become dependent variables. So we have another function you can kind of calculate. So calculate is not for the minimization of energy, but for the given internal degree of freedom. So you can long equilibrium state, the energy of long equilibrium state. And Richard did great job for developing this code. And after graduation, he moved to JPL, NASA. And he continues to develop it. And then he put this software for competition for NASA Software of the Year in 2019, received a 2nd place. So I have to think about this one, right? This is NASA-wide software competition, include all software engineers, okay, across NASA. And I really think Richard did a great job and to make this CALPHAD programming and demonstrated its impact to NASA. So as I mentioned, we had workshops. So we have next workshop on CALPHAD aspect. It will be next week. It's offered by Massachusetts General Foundation and Pennsylvania State University with support from IBM. IBM is going to provide the cloud computing for the workshops. And it will be complementary to the participants of the CALPHAD Global, this conference. And the registration website is here. Hope you take this advantage and to participate in the workshop. It will be around 2 days, Monday and Tuesday in the mornings in the Eastern US time. So now we put this together, right? We'll put the machine learning, we'll put our MPDD and the CALPHAD aspect together, we'll build this ocean of data. We call it CODA. Want to bring all data together, okay? We can use cloud-based MongoDB database. Now it's hosted at the Penn State Virtual Machine. And we are going to develop a Optimate API. So Optimate is a new a kind of interface to connect the different databases. We find it very exciting. So we want to do that too. So people can access our data on our databases, and also tools too. Okay, so now we've got everything all together. Now what's next, right? So this you can, as you can see, that it will not take us 50 years, right? Hopefully next 2 or 3 years, we have all the structure, all the infrastructure set up, and the database can be more efficiently developed, and it can be efficiently updated with uncertainty quantifications. So now you can really design new materials. Okay? So as Greg also mentioned before, talk about the design with CALPHAD. We call it, I think that's called a rational design with CALPHAD. The idea is that with the knowledge we have, and we kind of not guessing, but we get some ideas about the composition range. Then we do the calculations. Okay? We do design, okay? And then we go through the circle. Okay, so it's called rational design. Is using human intuition or knowledge to change the input variables until the desired output is obtained. The question is, can we do better? Can we do it faster, fewer iteration? And can we improve the even better materials, right? Get better materials, okay? The idea would be, of course, as you would guess, is machine learning, right? So we talk about machine learning, generate data and do the modeling. But can we use machine learning to do the design too? So actually it's possible. Well, at least under development. It's called the deeper generative learning. And we talk about the machine learning, people usually in the black box, right? Like a typical social science, right? You have no models. But we, as Greg also mentioned, we have physics, we understand it. So we really want to do physics-informed machine learning. We're called PIDL models. And we are working with Professor Jun-Chao Xu at the Department of Mathematics at Penn State. He has been doing machine learning for a long time. We are working on a project to take his expertise, apply it to materials. It's physics-informed machine learning models. And then you get models, but it's still not enough, right? We need to do the inverse design. Okay, so it turned out the machine learning community, of course, is doing that too. So the one we're going to work on is called a conditional generative adversarial networks. It's called CGAN for inverse design. And our department had a new hire, Professor Wesley Reinhardt, and he's expert in that area. So we're working on that, working together. And on one project already from API to do inverse design of what, in this case, is refraction errors. Okay, I wanted to let you know that we do have recorded the presentations on these topics. And again, you know, this presentation will be online. I don't know, it's a PDF online too, so you can click it and watch those videos we had. Okay, this is just 1 or 2 slides about this called the generative modeling. Of course, as you know, I'm not an expert at that one, but there are a lot of experts. For example, this book by David Foster, Generative Deep Learning. So it introduced the mathematics and include hands-on practice on this book. And, you know, nowadays we're into the Python programming, use Jupyter notebooks to run your calculations. Okay. There are a lot of publications recently, even after this book, and they just see how fast this field is moving. I'm going to give a very simple, my understanding of this process is that it's really called latent spaces and the data abstraction. We know that the materials properties are determined by so many variables, right? So many variables. So it's impossible to look at all the variables, okay? But we can do the abstraction of these ones. Give you an example here is that, for example, look at this one, right? Look at this curved space here, right? Okay, but however, okay, if you flat it, it actually becomes much simpler, right? Much simpler, okay? It's much simpler than before. And you think about this one, in this space, these two are the nearest distance, but actually it's pretty far here in this space. Okay, this space. So the latent spaces are low-dimensional representation of high-dimensional data. You can see, but this is high dimension, this is low dimension, right? So you want this one, so this can be represented. I just showed here 2D manifold from 3D space. Okay. You can see actually this three-dimensional space only has 2 dimensions, even though it looks like 3 dimension. Okay, the idea is that you flatten high-dimensional data. Okay, to extract what to think of the meaningful features from raw data. So that process is the machine learning process. Okay, so just to give a little bit of understanding of my understanding of the neural network, right? Neural network actually is pretty simple functions. It uses a linear function, kind of linear transforms, and then there you have the, so that's what you get is functions here, okay? And then to the activation, okay? Another function is nonlinear, so I have linear and nonlinear, called activations. So Professor Xu gave me a lecture a few years back at one of the lunch we had together about this linear transforms and nonlinear activations. Okay. Now, if this looks very simple, right, for this one. However, if you put all of them together, okay, you put a lot of them together. So you can actually approximate any functions almost, okay? You can approximate all functions, okay? So the idea is really that you could put so many this kind of linear transformers and these activations together. They can basically mimic all kinds of functions. So why that works is because why it works and efficient, right? You have so many networks, so many nodes there, neural nodes, they're still very efficient because the linear transforms are very fast. Okay, nonlinear activation introduce complexity. Okay. And you put them together, stack them together, multi nodes and multi levels. You can basically reproduce anything. Now you will put physics into it, right? So we're going to talk about specific networks for our properties, what we want. So that's what we're working on. So that's what I think would be next 50 years. And of course, it has been demonstrated that works, right? So I think the next many years we're going to have is a inverse design workflow. Again, that's created by my colleague, Professor Ringhart. Okay, so for materials, right, we're going to train this neural network model and known composition and the property pairs, right? Knows composition with those properties. Of course, in the middle, we're going to have something more in the middle, right? What do we have middle? Of course, we know the faces, right? It's property of the faces, okay? So by pair this composition and property, and when we know the faces, then we can get the latent space of the connection. Okay. So basically, we have the conditional input and to neural network, and we're getting this latent space built up. Okay. And then we can specify each property or isolate the profit we want to optimize. Then we can propose the candidate materials based on the problem we need. And in that case, we're including the computation screening first. We do the prediction, then we do the computation, just like the rational design, right? And then we do the down screening, the down selection from computational, and then do the synthesis. Okay, so the idea would be that it would be much faster. It goes to the space which you may not have in there before. All right, so if you put it all together, that's the ocean of data. It's an ecosystem. As we know, that ecosystem never ends, right? It's an evolution process. You get new data, you get new property, you get new materials, then you get new data and new materials, new property, then you design new data, design new materials, right? This process never stops. Now we get better materials, more efficient to make the materials, and they have better properties. All right. With that, I want to thank you for your attention.